Hello and welcome to our virtual senior design presentation. The title of our project is the Gas Turbine Test Bench. My name is Carissa Henning and my fellow group members are Bradley Solomon, Brian Ayala, and Matthew Day. For this project, Dr. Parthipan is serving as our client, and he currently has a 1989 military-grade gas turbine located at the PDRC. The purpose of our project is to modify the current system and prepare it to be utilized for future research purposes. The objectives of this project are separated into three phases. Phase 1 being mechanical design. During this phase, the existing turbine cart and fuel system will be analyzed and modifications to both systems will be proposed. Our customer would like these modifications to be made so that the turbine itself is more accessible, stable, and allow for potential noise dampening. The second phase will consist of the controls. This phase will analyze the current analog system and propose modifications necessary for the conversion to a digital control system. Along with the new digital system, mechanical fabrication of the modified turbine cart and fuel system will begin. Lastly are the instruments and measurements. During this final phase, the group will be required to insert 2 new sensors that will provide useful data readings for Dr. Parthipan's future research. The timeline of our project is separated into 3 parts relating to each of the project's phases. Phase 1 being mechanical design, Phase 2 the control system, and Phase 3 instruments and measurements, along with testing the system as an entirety. Within each phase are specific project goals to achieve by the established date. To begin Phase 1, the existing system must be analyzed. Pictured are the frontal and rear views of the gas turbine cart located at the PDRC. The current analog system is controlled at the control panel shown. The generator and control system run using the generator electronic control module and the engine electronic control module. These 2 components will no longer be of use once the digital control system is created. Based on the objectives previously stated, there are 4 main components that play an important role through the course of the project. This being the fuel tank, engine housing, exhaust door, and the fuel system.
The proposed mechanical modifications of the turbine include the removal of the JP8 fuel system, removal of the trailer hitch, reframing of supports, increasing turbine accessibility, and updating the sound insulation.
2 designs were proposed for the turbine cart. The first design features a sliding door panel for access to the turbine housing and rests on 1 single central support. Design 2 uses a hinged doorway to enter the turbine housing, but is stabilized by 2 double supports on either side of the turbine cart.
Design 2 was chosen as the optimal design based on customer preference and as it provided more stability, reducing the chances of tipping. The hinged door also made it easier for a client to access the turbine housing. To find the critical locations of design, a shear and bending moment diagram were created using SkySoup on the top beam of the supports. As you can see in the middle, the max bending moment is reached right at the center of the beam, making it our critical location. The max bending moment was then used to find the principal state of stresses and the maximum shear stress to calculate a safety factor of 9.47. Buckling analysis was also performed to find the critical force for buckling occurs. This force was calculated to be about 320,000 pounds, with the actual force being around 176 pounds. Here you can see the final completed turbine cart, with the front hitch and fuel tank removed, the supports at the bottom, and the door cut into the front panel for easy access.
Our group decided to create a separate fuel cart so the tank and the fuel components can easily be pushed out of the user's way. A few fuel cart designs were considered, but reusing the trailer hitch and modifying it was the best option. Wheels will be added in the rear, and a panel would be added to the side of the tank to accommodate the fuel components. A fuel quick disconnect and an electrical connector will allow the user to connect and disconnect the fuel cart to the gas turbine as necessary. In the future, research will be conducted by replacing the JP8 fuel system with a hydrogen fuel system. By removing the JP8 fuel system, the user will have increased space, access, and safety when working with the new hydrogen fuel system. Here's a figure showing all the connections necessary for the fuel components. The black line represents fuel flow and the red line represents an electrical connection. To connect the fuel components together, AN-06 braided fuel line and fittings were used, and a quick disconnect was used to attach the fuel system to the turbine itself. Electrical components were soldered to a PCIe connector to then be connected to the turbine itself. This is the final design for the fuel cart. In the design process, it was determined that creating a horizontal base for the components would be more appropriate, as orientation mattered for some of the fuel components, and a horizontal base would better accommodate this. Wooden supports and casters were mounted in the rear, and the fuel tank was secured in its original position with brackets instead of welds.
The existing control system utilized two controllers to operate the generator and the engine: an engine electronic control module and the generator electronic control module. Both devices communicated with each other and used that information to alter the performance of the engine and generator to prevent any failures. The existing control system was originally designed in 1987. Problems with the existing system include that it doesn't display real-time data performance for exhaust temperature and engine speed. And due to the age, the user is unable to modify the control system to operate the engine as he pleases. 4 controllers were considered in order to select the optimal controller to operate the system: the Raspberry Pi 4B, the MyRio, the MyDock, and the Arduino. Each controller was compared based on 5 criterion: customer preference, programming easeability, analog inputs and outputs, price, and digital inputs and outputs. Each criterion was given a weight from 1 to 5 based on its importance, and then all of the controllers were then graded based on the criterion weight. As you can see, the MyDock and the MyRio both received a final score of 15. So a second Pew matrix was used to determine the optimal device between those two. The price was compared, the digital input-output lines, and the device communication was compared. As you can see, the MyDock has a price point of roughly $200 less than the MyRio, giving it a slight edge. However, the MyRio has over 40 digital input-output lines and can communicate with the host computer over Wi-Fi, allowing long distances between the host and the device while operating a control system. A little bit of background information about the MyRio device. It's manufactured by National Instruments. They make a lot of controls devices for students and industry professionals. The device is programmable through their programming software LabVIEW, which is a visual programming language. The MyRio device is capable of sending digital I/O, analog I/O, audio, and power output. It has an onboard 3-axis accelerometer that is capable of displaying real-time data. Each analog output channel has a dedicated digital to analog converter, and the MyRio can generate analog signals up to plus or minus 10 volts. All digital lines can be programmed as either an input or an output channel, and each digital line offers either a 40 kiloohm or 2.1 kiloohm pull-up or pull-down resistor. This is a one-line diagram of the proposed control system for the engine. All devices would communicate with the MyRio, including the transfer fuel pump, high-pressure fuel pump, fuel solenoid. All of these devices are located in the fuel cart, and devices in the engine that would communicate with the MyRio include the exhaust gas thermocouple, monopole speed sensor, engine starter, and the ignition exciter. All of these devices would be controlled by a master switch via a new control panel. Sensors that will relay information to the MyRio device include the exhaust gas thermocouple, which will notify the user if a combustion in the engine is successful by detecting a change in temperature, the monopole speed sensor, which will detect the speed of the engine and relay this information back to the MyRio, which will then be processed through a PID control loop and used to control the output speed of the high pressure fuel pump, and the fuel volume, which will just notify the user if the fuel volume in the tank has gotten too low. Electrical components that were added to the control system include an 8-channel relay module. A relay module utilizes an electromagnet to open and close a switch. When a 5-volt signal is sent to the channel, the electromagnet will energize and close a switch. The port breakdown shown in the middle is the normally closed, common, and normally open. For our case, the 24-volt line was connected to the common port, and the line that would go back to each engine component, such as the engine starter, would be connected to the normally open. When a 5-volt signal is sent, that magnet will energize and the switch will close, allowing power to flow from the common node to the normally open node. The H-bridge shown on the right was utilized to control the speed of the high-pressure fuel pump. When a PWM signal is sent to the H-bridge, the voltage will vary, that is output from the battery to the motor.
The starter solenoid, as seen in this photo, receives power directly from the battery. The positive and negative terminals are the terminals we connected two 640 amp 12-volt batteries in series to achieve our desired 24 volts. Also, from the positive and negative terminals, a positive lead wire was extended to positive terminals of 24-volt components, while a negative lead wire was extended to the relay switch board to serve as a signal wire for the same 24-volt components. The colors on this photo are slightly deceiving and were later changed, but the negative lead from the battery was spliced and plugged into the center common terminal on the first 4 relays, and another wire from the normally closed terminal will run to the negative terminals of the appropriate component. The relay board and therefore the fuel components could then be controlled by the MyRio. The H-bridge speed controller, as seen on the left, works in a similar way, but rather than just controlling one terminal, both terminals are controlled by the H-bridge, and a throttle can be imposed rather than just an on and off switch.
Using the LabVIEW programming software, an initial code was written to control the engine components. The image on the right is a sample code used to control the flow of fuel into the engine. When the Boolean toggle switch is shown on the left is put into the true position, power will be supplied to the low pressure fuel pump, fuel solenoid, speed sensor, and thermocouple. If the switch is put into the false position, all power to these components is disabled. The return signal from the voltage from the thermocouple is processed through the LabVIEW thermocouple function. Inputs into the function include thermocouple type, circuit type, CJC voltage adjustment, signal reference, and output units. Outputs include the thermocouple temperature reading displayed as a numeric indicator and a gauge. A second toggle switch was used to control the engine starter and ignition exciter. If the toggle switch is in the true position, power is supplied to all components listed. If in the false position, power is deactivated to both components. The ignition exciter is on an elapsed time function. A target time of 10 seconds was set as the input. If the elapsed time is less than the target time, a high signal is output to the spark igniter relay module, allowing the ignition exciter to turn on. After those 10 seconds have elapsed, then a low signal will be sent to the ignition exciter, disabling its power. Using a PWM signal or pulse width modulation signal, we were able to control the speed of the high pressure fuel pump. The PWM signal fluctuates between 0 and 5 volts really quickly. The duty cycle is the percentage of how long the PWM signal is sitting in the high position versus the low position. For example, a 25% duty cycle the signal would be sitting in the high position 25% of the time and the low position 75% of the time. A PWM cycle of 1 would give the maximum voltage to the motor, giving us the maximum speed. By altering the PWM duty cycle transmitted to the H-bridge, we can control the speed of the high pressure fuel pump from either a very low speed to a very high speed. A PID control loop was used to control the speed of the high pressure fuel pump. The input into the PID loop is the speed value read from the monopole speed sensor. The output for the PID loop is the duty cycle strength of the PWM signal, ranging from 0 to 1.0. As you can see in the bottom of the image, the speed sensor is read through a tone measurements function, which will analyze the signal and output the frequency of it, which we then converted to RPMs. That value is then inputted back into the PID loop, where it is then processed and used to output the control of the duty cycle. An auto-tuning PID loop was utilized for the speed control. When the speed sensor begins collecting data, the PID loop will begin the process of tuning the proportional, integral, and derivative gains. The user can input appropriate boundaries for the PID gains that will result in the desired output response and error accumulation. An emergency stop protocol was programmed into the engine controls. This would allow the user to kill power to all devices, including the low pressure fuel pump, fuel solenoid, engine starter, high pressure fuel pump, and spark igniter, in the case of something going wrong. When the toggle switch is flipped into the true position, all power is killed and the engine will stop operating. The control panel shown on the right was generated to allow a user interface between the engine and the code. When the user flips either of the toggle switches shown on the left, the engine will start or the fuel flow will begin, or if the emergency stop switch is flipped, then all power will be killed to the system. A numeric slider is shown next to the toggle switches, which allows manual control of the speed of the fuel pump. The engine status section of the control panel displays information regarding the exhaust temperature and the speed of the engine in revolutions per minute. The bottom section of the control panel is the PID loop auto-tuning section. The output for the PWM range is set from 0 to 1, and the PID gains output is displayed after the auto-tuning process is complete. The first button shown on the right is for auto or manual. So if the user wants to operate the system using manual controls for the speed of the pump, he can press that button. If he wants to use automatic, then he sets that button to false. The reinitialize will just reset the PID loop tuning system, and the start auto tune, when pressed, will begin the auto tuning process for the PID loop. And the green LED light shown on the bottom will illuminate when the auto-tuning process has been completed. The startup sequence for the pump follows. The fuel pump PWM is set initially to 0.2. The engine start switch is flipped, which will allow the engine starter to begin and the ignition exciter will begin to ignite. Next, the fuel flow switch is toggled immediately after the engine start, which will open the fuel solenoid and allow fuel to enter the engine. As the starter motor increases speed, the value of the PWM signal is increased to 0.5 manually. Following the ignition of the fuel, the engine starter motor is disengaged. At this point, the user can begin auto-tuning the PID loop. Lastly, once the auto-tuned PID loop has completed, the PWM output is changed to automatic from manual, allowing the PID to adjust the speed of the fuel pump to maintain a desired revolutions per minute.
For the sake of safety, all electrical components were routed to and stored in the old EECM compartment away from the field components. A makeshift wiring harness was created as part of it is seen in the photo in order to manage the many electrical component wires that are scattered throughout the engine bay. A new wiring color system was also employed, red for positive, black for negative, and yellow for signal wires.
In order to successfully test the system as a whole, it was important to test the components individually to determine functionality. The fuel system by far was one of the most important factors in the project. In order to achieve a result of exhaust being created, the igniter in the turbine has to light a fuel being supplied. If the system does not correctly deliver fuel, then the turbine engine would not function properly. Therefore, the first test needed to complete was the fuel flow from the tank through the solenoid and into the turbine itself. The remaining tests contributed to the digital control system. The relay module and H-bridge devices connected the components to the MyRio, which was then controlled electronically. In order for signals to be successfully delivered to the components, it was important to test the individual connections. If these connections were successful, it meant that the components were functioning properly and they were ready to test as a whole. Lastly was the implementation of the sensors. The sensors were the easiest additions by far because once they were wired, the data would instantly be sent to the MyRio to be monitored. As the group began testing, a slew of problems arose. To start, the fuel system wasn't correctly delivering the fuel into the turbine. This was discovered by testing the various components of the fuel system. Initially, the fuel wouldn't even pass through the low-pressure fuel pump, and that pump was the first connection from the fuel tank, which meant that none of the other fuel system components were receiving fuel. A second issue was severe amounts of fuel leaking before and after the solenoid connections. This meant that there was a lack of fuel actually being delivered into the turbine, if any at all. The remaining issues stemmed from the control system. The group tried several combinations to start the components to achieve a result of burning the fuel and converting it into exhaust. However, the starter sequencing was wrong and the amount of fuel delivered to the turbine was either too rich or too lean.
To fix the wiring issues, a digital multimeter was used to check the voltages at all terminals and assign polarities. Several attempts were made to fix the low-pressure fuel pump, including priming the pump, adding additional fuel to the tank, and laying the pump below the fuel tank to avoiding the head. A correct gas turbine engine sequence was referenced to help ignite the fuel injected into the engine.
So in this little clip of the turbine running, you'll get to hear 3 tones. So the first tone is the starter beginning to compress air while nothing has combusted yet. The second tone begins as combustion occurs and the turbine generates speed. As the generator builds up to and past a sustainable speed, the starter resists the turbine from spinning faster. So the third tone begins as the starter is disengaged and the turbine is free to accelerate up to its max frequency. As a bonus feature, the following video shows an attempt to run the turbine by first injecting fuel for a window of time, then running the starter, resulting in a super rich air-fuel mix to be ignited. Enjoy.
Top one?
Yep. Yeah.
Thank you for watching our virtual presentation, and please feel free to ask any questions you have during the Q&A phase.